Hello, students. This is Mr. Reynolds here with some notes. Finishing up the quantum physics section, we're going to sort of tie a bow on all this, talk a little bit about electrons and how they're waves and particles, and hit the final topic, which is the Heisenberg uncertainty principle. We will be in topic 12.1, so it probably is helpful to be looking at your data booklet during this time. There are two equations for this topic. However, the two equations are very, very similar. You don't need to know how to derive them, and they are pretty straightforward for how you're going to use them. This is not a topic that's going to be asked in any some kind of electrical circuit section or something like that. It's going to be a pretty straightforward kind of problem. And after I finish this, I'm going to have you read the book and try some of the problems where they use these equations and let you sort of see how they all work together. So let's start by just sort of refreshing our memory on what an electron is. What we found via a couple different methods is the electron has two natures. The electron can act like a particle, and the electron can act like a wave. Now, the particle part of an electron is pretty easy to imagine. It's something that has mass, it's something that has size, it's something that scientists have thought about it as a particle for a very long time. We can detect it, it hits things, all sorts of things like that. The wave nature of the electron was found by firing these electrons through thin sheets of maybe a crystal or a graphite or whatever, and seeing a diffraction pattern occur, seeing those electrons form a weird kind of pattern. Now, scientists were a bit baffled by this. Scientists did not understand at first how an electron could be a particle and a wave at the same time. And in fact, there's a lot of debate about this. They just were not sure what was going on. They had conferences after conferences and talked about it. Eventually, they came up with what was called the Copenhagen interpretation. Okay, so this was something they did in Copenhagen and all this kind of stuff. And they decided that the electron behaved like this. So when the electron was in normal fashion, the electron behaves like a wave. In normal fashion, the electron behaves like a wave in that it moves around. It doesn't have a defined position, perhaps. It does diffraction, does all these sorts of things. Only when the electron is being detected does it then become a particle. Well, let me give you an example. So let's imagine a double slit. A double slit experiment here. Where, again, very, very narrow slits, very close to each other. I fire electrons through these slits. Now, what happens is, while the electrons are traveling through the slits and while they're in all this area over here, they're behaving like a wave. In that these electrons really are everywhere. They're spread out. In fact, there's so many different possibilities of where those electrons are. This wave function we talked about is actually sort of the sum of all the different possibilities of where the electron could be because it's behaving like a wave. Now, once the electron hits the screen, all of a sudden now the electron is detected. Okay, it hits the screen, it is detected, and at that point it becomes a particle. All the different possibilities of where the electron can be all collapse, and you're only left with this particle-like electron only being in one place. When the electron hits the screen, it's in one space. It's not anywhere else. Now, some people had a strange reaction to this. The idea that the electron had infinite numbers of possibilities until it was detected, and at that point all the possibilities would collapse on themselves. And one of the big opponents of this plan was a guy named Schrodinger, and he came up with a thought experiment. This wasn't a real experiment, don't worry, called the Schrodinger's cat experiment. So he put a little kitty. Do not mock my cat drawing skills. This is exactly what a cat looks like, or a brat, or I don't know, but it's a cat. Let's just imagine it's a cat. This cat is sitting inside a box. Inside the box, we cannot see, we cannot measure, we cannot detect anything inside the box. There is a radioactive isotope that will decay at some point. We know radioactive decay is a random, spontaneous process. We don't know when it's going to happen, but we're going to give it one half-life. There's a 50-50 chance it decays. If it decays, it will release a dangerous gas. So like, anthrax or coronavirus, let's say. It will release coronavirus onto the cat. Okay, horrible, horrible situation. And the idea that he put forward, mocking the Copenhagen interpretation, was that he said, after one half-life, even though we can't see the cat must be either A, alive, or B, dead. Those are the only two options. We can't have all these different possibilities, and maybe the cat's alive and dead at the same time, and they all exist in one place until, boom, we open the lid, and all those possibilities collapse on themselves and let us see if the cat is alive or dead. Okay? He said very clearly, this is a foolish idea, and here's a thought experiment that proves how foolish it is. Well, it didn't work the way he thought, and now this Schrödinger's cat example is given as a very common example of the current thought of how quantum physics works. I believe you kids would call it the ultimate flex on someone who did not believe the Copenhagen interpretation. But that is something that happens. It's sort of weird. I sort of want to point that out. I do find it really interesting that the Schrödinger cat, which everyone looks at as a great analogy of quantum physics, was put forth as a repudiation, a example of how it can't work, which is sort of didn't work the way Schrödinger thought it would. Now, when we see this electron going through the slits here, something sort of interesting happens. And one of the things we sort of found out through this Copenhagen interpretation, we came up with this idea called the Heisenberg uncertainty principle. Heisenberg uncertainty principle. And really the definition is best left as an equation. And essentially what the Heisenberg uncertainty principle says is you can know the position of an electron very well, or you can know the momentum of the electron very well, but you can't know both at the same time. In order to measure the position to a high degree of accuracy, you would need to disturb the electron, which would affect its momentum, and vice versa. If you were going to detect the momentum, you would have to do something to the electron, which would cause it to move, and now you don't know where it is. And so the basic equation we have for the Heisenberg uncertainty principle is going to be found in 12.2 is delta x, delta p, is greater than or equal to h over 4 pi. Now, you'll notice on the right side of this equation, you have constants. H is a constant, 4 is a constant, pi is a constant. And so what they're saying is, if you take the uncertainty in the position of an object, multiply it by the uncertainty of the momentum, that product has to be bigger than or equal to this value right here. Let me give you an example. Let's imagine an electron going through a really narrow slit. Okay? Electron is going through that very narrow slit. While the electron goes through that very narrow slit, we know where the electron is. It's got to go through the slit. And so we could say that delta x in this case is the width of the slit. We know it has to be somewhere in the realm of that opening. Now, because we have the uncertainty of the position very low, because we know where it is very well, the uncertainty of momentum is very high. Now, where does that manifest itself? Well, the electrons are coming into the slit, traveling to the right, traveling horizontally to the right, let's say. But as the electrons come out, they might not be traveling to the right. They had a momentum to the right. There's your momentum traveling to the right. But now they might have some uncertainty in the momentum. Maybe it's changing momentum up. Maybe the electron has some momentum downwards. And so by forcing the electron through more and more narrow slits, by making delta X smaller and smaller, the change in momentum and how far that electron is going to spread out or diffract gets bigger and bigger. This is the Heisenberg uncertainty principle, and it's proven out pretty well through experimentation. Now, let me explain how you're going to use this equation, because it's usually pretty straightforward. You see that nice little inequality. We always hate using inequalities in equations, and I'm here to tell you, don't worry. You're never, ever going to really use that inequality. One of the things they're going to give you is they're going to give you something like this. Let's imagine they give you a graph of the wave function. And they say, hey, the wave function of this electron is like such. Okay, there's our wave function. We can tell that the electron is likely to be here, or here, or here, or here, or here, or here, somewhere like that. But there's our wave function. And what they're going to do is they're going to give us the distance. The distance from one side of the wave function to the other, we'll call that L. And so I look at this graph, and they may ask you a question saying, well, okay, here's the wave function of the electron. What is the minimum uncertainty of momentum? What is the minimum uncertainty of momentum? And so the way you work it is you use that Heisenberg uncertainty principle. Let me show you here. Delta x, delta p is greater than or equal to h over 4 pi. And let's go ahead and solve for delta p. Delta p is greater than or equal to h over 4 pi delta x. Now, the question was, what is the minimum uncertainty of momentum? And so what would you do with that inequality if you were to find the minimum? And almost always what you're going to do is you're going to set that inequality to an equal sign. You're just going to set it to the equal sign because, delta p can be anything bigger than this value. So how can I ask you to solve for what that bigger value might be? No way to really do that. So we're just going to simply say delta p equals h over 4 pi delta x. And then you just do your math. In this case, delta x is L. Because I know that electron must be somewhere within that length L. And that's a lot of times how you're going to solve the Heisenberg uncertainty principle. There's another version of the Heisenberg uncertainty principle that you don't use a lot. We may talk a little more about it next week when we start studying particle physics. And that is, it's very similar. Delta E, delta T is greater than or equal to h over 4 pi. You can probably see the similarities here. This is for things decaying. This is for reactions between tiny particles, fundamental particles. And again, we're going to talk about things like pair production and stuff like that a lot more next chapter. If you're reading the book, you're going to see a section on pair production where they're going to talk about some things and they're going to make you very confused. Let me go ahead and be the first to tell you, don't worry about that right now. We're going to talk about pair production and pair annihilation, which is actually a sort of neat little topic. We're going to talk about that next week. So I'm not worried too much about that at this time, but you can see delta E, delta T. If you see some kind of problem where they're saying, hey, the uncertainty and the energy is this, what's the minimum uncertainty in time? Just solve it like we did above. Really not too bad. What I'm going to have you do is I'm going to have you read the section in the book. The instructions will be in the document. I'm going to have you worked examples out, and I'm going to post another video with me just working out those worked examples, just letting you see sort of how it all works out. So hope you enjoyed this video. If you did enjoy the video, I hope you can visit our sponsor, Casper Mattresses. Casper Mattresses, boy, I'd really like to have one. So visit casper.com/ReynoldsRocks. That may or may not work. I don't actually know. Probably doesn't, honestly. Also, make sure you subscribe. I'm only like 999,990 subs away from that golden YouTube subscriber thing. And make sure you hit the bell. So, the YouTube algorithm really makes sure you see all these videos at the top of your subscription feed. Take a look at the book. Hopefully you understand this well, and I look forward to speaking to you next time. Thank you.